Hello. Today we are going to do a few new topic that is called as. Today we are going to do a new topic that is called as your Green's function, and this is a very important topic because you'll find Green's function time and again appearing in several boundary problems in physics, especially for people working in scattering theory, and it is an important topic for them. Further, you can see that in previous year examination also, in net examination, all other such examination, you'll find that these functions are being asked time and again. The questions regarding these functions are asked time and again. So, what would be the way ahead to do all these things? Would be the first thing that we are going to do is we are going to see all these things uh, in perspective of only solving a boundary value problem. And lately, as we will move ahead in this particular topic, we will also try to see some of the applications and some of the physical insight that I can have with the Green's function, especially in electrostatics and scattering theory and relevant topics. Okay, so this is what is my endeavor, and what I would do is I would go, as I told you, I'll start with very basics. That is, I'm not going to give you any sort of motivation initially. I'm just going to start very plainly with what is Green's function, how to solve a differential equation, how to solve a boundary value problem initially. And once I have developed that kind of approach, then we'll see some of the physical applications so that it gives you enough motivation. Okay. So first thing up, let us start with Green's function. Okay, let us start with Green's function. So Green's function. Okay, so you can see that like uh, in theory of you can say ordinary differential equations are simply differential equations. In theory of differential equation, an important role, an important role is played by certain mathematical objects, like by certain mathematical objects called as Green's function. Green's function. Okay, so obviously I can say that they form an important rule because they serve as some mathematical characterization. So for several applications, they serve as a mathematical characterization of some important physical concepts. So important physical concepts, physical concepts. Specifically, I would mention electrostatics and quantum mechanics. Okay, in quantum mechanics. Okay, so today we are just going to, from today we are starting it. So we are going to just begin it with less physics and more of mathematics. Initially, my target is to make you quite friendly to these functions and to solve the boundary value problems using these functions. And when we are done that way, then we'll try to solve some of the physical applications of the same. Okay. So let us start with something called as today with the boundary value problem. So okay, if what do you mean by IVP? So I'll just give you an example. Like I'm not giving you a rigorous definition, but just an example. So for example, if you have this dy by dx given as f of x, and at x naught, you have some y naught value. So if I say that what is the value of fx naught, let's say it is y naught. So if your differential equation is defined and some initial condition is imposed on, some initial conditions are imposed on the functions, are imposed on the functions on f. Okay, then I would say that you can say that this particular differential equation is it forms an IVP. But if these conditions are imposed on derivatives also, if the conditions, sorry, given that y of x naught is some y naught, and if these conditions are imposed on the derivatives also, then I would say that this forms a boundary value. I'm not giving you the exact definition, but just trying to uh, make you accustomed to the word, because I'll be quite frequently using this word called as boundary value. Okay. So let us first start with examining a second order differential equation with some initial conditions given. So let us first examine a problem given by this particular differential equation. So whenever I write L y, it implies I'm writing a linear differential operator. Okay. However, I'm not writing it. I'm starting it quite basic, so I'm not going to use it. But if let's say if this is the case, d2y upon dx2 plus let's say a1x dy by dx, and let's say this is a2x y, and let's say it is equals to f of x. So whenever f of x comes here, this is called as inhomogeneous differential equation. Because if your fx is 0, then you have something called as homogeneous differential equation. But if fx is not 0, this is called as inhomogeneous differential equation. Okay. So if you have some inhomogeneous differential equation, this can be as well as written as L by f of x. So whenever I write L, just don't get confused. L would mean d square plus a1d plus a2. This is what your L would mean. This is called as your linear differential operator. Is that clear to you? Okay. Now, let us first examine a simple, I'm not going to write it in this format, but if at all I write somewhere in this format also, don't worry about it. So probably if you see Arscan and Weber, that is a book on mathematical physics, probably they would start with L. I mean, that is how they do. So don't worry about this. This is simply your linear differential operator. Okay. So let us first examine a linear differential equation, second order linear differential equation. You can say consider a second order homogeneous linear differential equation. Homogeneous means you do not have this particular function. You have 0 there. So I'll start with a basic problem, that is p1x dy by dx. And then you have something called as p2x y is equal to 0. Okay. So if you have this problem, and given the conditions that your alpha times by a minus beta times y dash a is equal to 0, and gamma times by b minus delta times y dash b is equal to 0. So if you have these two conditions where your alpha, beta, gamma, and delta are non-zero constants, here your alpha, beta, gamma, and delta are non-zero constants. So these are the conditions given on the derivative and on the functions also. So obviously this particular problem would also be called as your boundary value problems. You have a given boundary value problem, which happens to be a second order linear differential equation. And here I can write that my p0, p1, and p2 will be some continuous functions of x. So p0, p1, and p2 are continuous functions of x. Okay, so p0, p1, p2 are continuous functions of x, and alpha, beta, gamma, and delta are non-zero constants. So you have this non-zero constants, and this p0 d2 upon dx2 plus p1 d1 by dx plus p2y equal to 0. This is your second order homogeneous linear differential equation. Now we say that a function g x comma zeta with the following properties. We say that there is a function g x comma zeta with following properties. And these following properties, and this particular g is called as your Green's function. This particular function is called as Green's function. Okay, we'll see the motivation, the physical motivation we'll see in quite a while. Like in few lectures later, I will try to develop that particular thing also for you. But right now, just try to solve boundary value problem using a prescription that I'm giving to you. Because once you are able to do all these things, only then you'll be able to figure out. Like for example, when you were a student, initially you were taught linear differential equation of first order in standard 12th. When you were doing BSc in mathematics, or probably you had a mathematics minor, or anyway, if you had somewhere mathematics, or even if in physics also you were doing some second order differential equation, then you did not have this motivation key we are going to solve some oscillations problem of oscillations in physics. So initially we were taught how to write the solution, and then we were able to figure out the physical applications. Similarly, I'm taking this approach in Green's function because I don't want to go directly rigorously into the physics part and make you understand Green's function. First, I want to develop how to write Green's function for a particular boundary value problem. This will be my initial stuff. And then as I move ahead in the lecture, you'll be able to figure out using different other applications that how for a particular problem, Green's function could be written in physical realm also. But right now, the approach that I'm taking is quite mathematical, so kindly bear with me. So function, this particular function is called as Green's function, and it satisfies the following properties. The first thing that it does is it satisfies the differential equation itself. So I will write here that gx comma zeta. Just don't worry about it. I'll explain this. This is so basically Green's function will have x, and there would be some other zeta also. Sometimes in books you'll find written as s also. So gx comma zeta satisfies the following property. The first property it satisfies is it satisfies the differential equation itself. So the differential equation whose solution we are wanting to find using Green's function. So first thing is that this particular Green function would satisfy this particular differential equation itself. Okay. Okay, first thing is this. Second thing is, and we are doing it for homogeneous case first off. Don't worry. No? So we are doing it for homogeneous case. So here you do not have any function. So we are doing it for homogeneous case. First thing. Second thing is, gx comma zeta would satisfy the boundary condition as well. So I should write satisfies the homogeneous boundary conditions as well. Homogeneous as well. Okay. So what are the boundary conditions? The boundary conditions given were alpha ya minus beta y dash a. So I'll write alpha ga comma zeta minus beta g dash. I think it was a comma zeta y dash, and then I had some gamma, and I had this b comma zeta and minus delta g dash b comma zeta is equal to 0. Okay. So this is one other thing. Third thing is gx comma zeta is also a continuous function. Is a continuous function for all x belonging to a comma b. So in fact, for all x belongs to a comma b, this will be a continuous function. So it will also be a continuous function for zeta. So basically, where your definition is parting, that is, you have two parts. Let's say what will happen is that whenever you are going to write x comma zeta, you will have two definitions. One will be for this segment, other would be for this segment. So if I write that my Green's function is continuous for all x, then it is also continuous for zeta. That is, if I write this way, that is, it is continuous for zeta. That is, whether you take the right hand limit to the zeta or left hand limit to the zeta, it is equal to the value of the Green's function at zeta itself. Is that clear to you? Bharat, is that clear? I mean, I know that.
Yes, sir.
है ना? अभी एक बार हम लोग क्या करेंगे, एक बार हम लोग पहले इसको सॉल्व करने की कोशिश करेंगे, समझ रहे हो? तो क्या होगा कि एटलीस्ट यू आर एबल टू फिगर आउट. I'll do a problem. I'll do a probably tomorrow itself. I'll do a problem, and then we'll see in electrostatics also and like quantum mechanics also. Tomorrow I'll do a classical problem, so that थोड़ा सा the relevance has it. But initially एक बार इसको बना लेते हैं. At least we should be able to understand कि Green's function करना कैसे है, Green's function construct कैसे करना है, Green's function की property क्या है. At least इतना हमें समझ में आता है initially.
Yes.
Okay? So this is my motivation. Fourth point I should write is, I think, okay. Fourth point that is very important. It happens that your Green's function, the derivative, the first order derivative becomes discontinuous, and the jump discontinuity that it has is given by some particular quantity that I'll write. Okay. So what will happen? So I should write. What should I write? Lico for any zeta in a comma b, gx gx has a continuous derivative in these like in each half of the interval, in each half of the interval, in each half of the interval it is continuous, that is not a problem, but is discontinuous at zeta. So each half of this interval, here here if you find the derivative, it will be continuous. Here if you find the derivative, it will be continuous, but it will be discontinuous at zeta. So at zeta, where this particular function is breaking, there you will find that your first order derivative is discontinuous. So first order derivative, here your function is of x. So I'll write gx. It implies I'm taking the partial first order derivative. You can say dg by dx also, because here, because you have two functions now, so therefore I'm using gx. That implies I'm taking the derivative with respect to x at zeta plus comma zeta minus gx zeta minus comma zeta, and this is equals to minus 1 upon, this will be p naught zeta, where your p naught is the coefficient of the highest order derivative that it exists. So for example, d2y upon dx2, here you have p naught x. So what I can say that my gx zeta plus comma zeta minus gx zeta minus comma zeta is equal to minus 1 upon p naught zeta if x is equal to zeta. So overall, you can say that this is what constitutes your g. So these are the properties that are of g. Is that clear to you?
Yes, sir.
Okay. So the following properties, for following non-differential, as for following homogeneous differential equation, this is your Green's function. Okay. So for example, if I give you a simple example, construct a Green's function for the following. So construct Green's function for the following. So let's say if I have this particular problem that you already know, whose solution obviously is going to be a straight line, that is d2 upon dx2 equal to 0, given that your y0 is equal to 0, and y0 is equal to y dash 1, and your y dash 0 is given to be y1. Okay, so all these property we are going to see. The first property that I wrote was that your Green's function, if at all it exists for a differential equation. Why I'm writing if at all? Because I'll let you know that what are the conditions, what are the necessary conditions, or in general, what are the conditions for the existence of the Green's function for a particular boundary value problem. We'll come to that topic, but right now I'm saying that this particular differential equation has a Green's function, and we want to find what would be the Green's function for this particular differential equations. This you know very well. Know this is a differential equation corresponding to the family of straight lines, isn't it? So d2 upon dx2 gives you 0. You just integrate twice, you get y is equal to mx plus c, or y is equal to ax plus d or something. So I know from the initial conditions that my Green's function, I will write, because you're starting this topic. So Green's function satisfies the differential equation. So if at all it satisfies the differential equation, then d2g upon dx square must be equal to what? It should be 0. Is that clear? And if it is 0, it implies what? It implies your gx can be linear function. So I'll write simply ax plus b for all x lying between 0 and zeta, and for all x lying from x, here your b is 1 and a is 0. So if x lies between zeta and 1, then let's say it is cx plus d. Is that clear? The first thing was that Green's function satisfies this differential equation. Further, you know that this Green's function also satisfies the homogeneous boundary condition. So you have these homogeneous boundary condition. Homogeneous boundary condition समझ रहे हो? मतलब y0 minus y dash 1 अगर लिखोगे तो equal to 0. So it is a homogeneous boundary condition. So if you see that, what would be this? This would be like writing would be equal to 0, and then it amounts to writing g dash 0 comma zeta minus g1 comma zeta equal to 0. So if I write these up, what I will get? So if g0 comma zeta, I have to write equals to g dash 1 plus zeta. So what is z dash 1 plus zeta? So this will be the derivative. So, for example, if I take g dash 1 plus zeta, what I would get? So if I use this condition, what I will get? I will get simply c here because the derivative here is c. And g 0 comma zeta means I'll get this. So it will constitute to writing b equal to c. Is that clear? What should I give this particular definition? So this is my 1. Let's say this is your 2. And this condition, this will give you, I think, a is equals to, and this will be, I think, c plus d. Is that clear? Is that clear? So for given this differential equation, the Green's function would obviously satisfy one, the differential equation. Secondly, the boundary value condition, the boundary conditions, like the conditions that were given to you. Third thing it would do is, I told you the third thing that it would do is that g would be a continuous function. So you can see that here is a linear function. Here is also a linear function. So you can write that this is a continuous function for all x lying between 0 and zeta. This is a continuous function for all x lying between zeta and 1. However, there may be a problem of continuity at zeta. So let me find whether my function is continuous at zeta or not. Is that clear to you? So I would write zeta minus comma zeta should be equal to g zeta plus comma zeta. Okay, so g would be a continuous function at zeta. So I should write, it will give me what? It will give me a zeta plus b should be equal to c zeta plus d. So this is your fourth condition. Is that clear? Now, the last condition that I told you was that the Green's function is actually continuous in each half of the interval. That you can see also. That if you take even the derivative, this is continuous. This will have a continuous derivative. So because you differentiate it, this particular derivative will come as a is a constant function. Here the derivative will be c is a constant function. So for all zeta lying between, for all x lying between zeta and 1, and for all x lying between 0 and zeta, your Green function will have a continuous derivative, but there will be a lack of continuity at the zeta itself, and that jump discontinuity is given by minus 1 upon p naught zeta. So if you write that particular thing up, so what you would get, you will get fourth condition, and that suggests that g dash zeta plus comma zeta minus g dash, I think zeta minus comma zeta should be equal to minus 1 upon 1, because your p naught here is 1. Is that clear? So if I write in that fashion, what I would get is, so the derivative to the left, I'll get c, derivative to the right, I'll get c, derivative to the left, I'll get a. So this will give me fifth condition, that is c minus a is equal to minus. So overall, all these 5 conditions together will give me some values of a, b, c, and d. Okay, so and that will give me the correct representations of my Green function. Okay, so let us first find. Let us write what would be the Green functions. First property was given to you was, I think, the first property is b is equal to c. Then you had, I think, c is equal to a plus d. Or sorry, c is equal to a is equal to c plus d. Then you had, I think, a zeta plus b is equal to c zeta plus d. And then you had, I think, c minus a is equal to minus. So you have all these 4 conditions, and you have to find what are the values of a, b, and c's. Okay. Is that clear? So Green's function is obviously a solution also to this differential equation. So you found that if Green's function satisfies this differential equation, so obviously this is also a solution. But lately we'll find that what will happen if my inhomogeneous conditions are given. So here you can see that Green's function itself is a solution to this particular differential equation. Okay, so now a zeta plus, now you just find me all these values. I'm giving you some minute. You just find me these values. Okay, you just find me these values. Okay, abhi kyunki Alpman abhi join kiya, मैं उसको वापस बोल देता हूँ. So देखो, we are doing something called as Green's function, and in particular we are discussing. I've already told that these functions are very important in electrostatics and quantum mechanics, and overall these differential equation initially, this Green's function we are initially examining for mathematical per se. So basically what we are going to do is we are going to just solve some boundary value problems using Green's function, so that at least we have some some idea how to construct Green's function for a particular differential equation or for a particular boundary value problem. So here we have this particular boundary value problem, P naught d2y upon dx2 plus P1 dy by dx plus P2y equal to 0. This is a second order differential equation, and given conditions alpha ya minus beta y dash a equal to 0 and gamma yb minus delta y dash b equal to 0, these are initial conditions. So whenever your initial conditions are given on the derivatives as well as on the values of the function y, these particular problems are called as boundary value problems. So in solving these boundary value problems, Green's function play an important role. So let us see how. So this is a homogeneous kind of differential equation where you do not have any factor on the right hand side, where any function on the right hand side. Such differential equations are called as a homogeneous differential equations. And P naught d2y upon dx2 plus P1 dy by dx plus P2y equal to 0, it has been given. And the function is called as Green's function if it satisfies the following properties. The first property that Green's function satisfies is it satisfies the initial. It satisfies the original it satisfies the original differential equation. So basically, what it does it do? It satisfies this differential equation. One. Second, it also satisfies the boundary conditions. These boundary conditions are also satisfied by the Green's function. Third, this particular G is continuous for all x belongs to a comma b. So for all x belongs to a comma b, this particular Green function is a continuous function. So you will find that whenever we are going to write Green's function, we are going to divide it into two segments. One will be x line from a to zeta, and second will be zeta line x line from zeta to b. I'll come on to a very good application in physics, physics, or you can say mathematics in like in a day or two, basically. But overall, before that, I just want you to at least understand what is Green's function. So at least some step as to how you should evaluate a Green's function for a particular boundary value problem. So first thing that you have to do is you have to see that whether it satisfies your differential equation. Second, you have to see that whether it satisfies the homogeneous boundary condition. Third, you have to see that whether it is a continuous function or not. So Gx has to be a continuous function between a and b. And if it is continuous between a and b, you already know that if your G is continuous, then probability is that, because here the definition is changing, so you have to see at least that G is continuous at zeta. Okay. Fourth condition is that overall you will find that your Green's function has a continuous derivative in each of these half intervals. So here also you have this. If you evaluate your Gx, this particular derivative is continuous. Here also, if you evaluate your derivative of the Green's function, here also it will be continuous. But there is a lack of discontinuity, or there is a jump discontinuity at exact zeta. That is, that particular jump discontinuity or amount of discontinuity is given by minus 1 upon P naught zeta. And we were doing this particular problem, d2y upon dx2 equal to 0, and we are solving this particular problem. As you are aware that Green's function would satisfy the differential equation, which suggests that d2g upon dx square should be equal to 0, and g must be a linear function in that particular case. Secondly, it should satisfy the boundary condition, which gives me these two conditions. Then g must be a continuous function for all x belongs to 0, 1 here in precise. So this will be this. And that the derivative of Green's function should be discontinuous at zeta. This will give me this. So overall, these are the conditions. I think, is that clear to Alpna? अच्छा अल्पना चलेगी, मैं तो फालतू ही समझा रहा था. So B is equal to C, A is equal to C plus D. अच्छा, आया भरत कोई आंसर है इसका?
D की वैल्यू 1 है.
चलो देखते हैं. I thought कि Alpna was there, so I was explaining all these things. चलो कोई बात नहीं. So this will give me D is equal to, I think, if I take there, so D would come as 1. 1 is, this is clear. If D is equal to 1, so if I write 1 here and C minus A, so this will give me the value of B. So B will be equals to what? So B will be equal to C minus A times of zeta and plus D. So B is equal to आएगा C minus of A plus D, and C minus A क्या आएगा? कुछ सोचो. C minus A minus 1, so it will be minus zeta, and this will be 1. So B is equal to 1 minus zeta. So B is equal to 1 minus zeta. If B is equal to 1 minus zeta, then C will also be equal to 1 minus zeta, isn't it? And if C is equal to 1 minus zeta, then I know that C minus A is equal to minus 1. So it will give me A is equal to C plus 1. And A is equal to, then 1 minus zeta plus 1. So it will give me 2 minus zeta. Is that clear?
Yes.
Okay. So overall, I know my Green's function for this particular differential equation would be what? It would be equal to writing A is 2 minus zeta, and you had this x plus b, 1 minus of zeta, and then I had, I think, c was 1 minus zeta x, and plus d was 1. So this is how you write your Green's function. So this is your Green's function for the given differential equation d2y upon dx2 equal to 0 and some conditions that were given to you. I think the conditions were y0 is equal to y dash 1 and y dash 0 is equal to y1. So this is how you write your Green's function. Is that clear to you?
Yes.
Okay. Now, I hope it is clear to you. This is how you write a Green's function for a homogeneous case. So another homogeneous case I'm just giving you. So another question that I'm giving so that at least you get how to write. So let's say another question that I'm giving to you is, let us construct a Green's function for the following differential equation. And this is a Cauchy-Euler differential equation. I hope you're aware of Cauchy-Euler. Otherwise, I'll explain you.
Yes, sir.
Okay. And the conditions are, one, that your yx is bounded as x tends to 0. And second, the condition is y1 is equals to alpha y dash 1. And alpha is given to be equal to 0. Okay. So if these are the conditions, that is y1 is equal to alpha dash y1 and alpha not equal to 0. And first condition is yx is bounded as x tends to 0. These two are the conditions given to you. And this is the differential equation. So just letting you know, this particular format is called as your Cauchy-Euler differential equation. So this we'll study in differential equation course. But overall, this particular format is called as your Cauchy-Euler differential equation. And what do? We just replace x by e to power z. And while I replace x is equal to e to power z, I get z is equal to ln of x. And if I try to write what is my dy by dx, so dy by dx I can write as dy upon dz and into dz by dx. So if I write my dz by dx, so by the given transformation, this particular thing would become 1 upon x dy upon dz. And if I want to write d2y upon dz dx2, this will be equals to d by dx of 1 upon x, and then you have dy by dz. So this will be like minus 1 upon x square dy by dz. And then you have, sorry, if you differentiate it, you just write dz upon dx. Okay, so if I write this d by dz, so this is dz by dx, so dz by dx I can write as 1 upon x. So this I can write as 1 upon x. So this will be, I think, 1 upon x, d by dz of 1 upon x, and then you have some dy by dz. Is that clear to you? So what I have done, if I have to evaluate my second order derivative, so it is like d by dx of dy by dz, dy by dx. dy by dx is 1 upon x dy by dz. So I've just replaced d by dx by d by dz, and here I've written d by dz. So d by dz by dx is 1 upon x, so forget about it. And then this is like d by dz of 1 upon x d2 d by upon dz. So what I would do, so I would simply do one thing. This is 1 upon x. And if I differentiate it, so again 1 upon x comes forward. So this is d2y upon dz2 plus again 1 upon x is here. If you differentiate it, so I will get what? I will get the derivative is minus 1 upon x square and minus 1 upon x square. I think I've made some mistake or something. So if I differentiate inside, what I will get? I think if I differentiate inside, I will get d by dx of 1 upon x, and I've written dy by dz, and then you have, I think, dz by dx. Okay. And if I differentiate it, what I will get? dx by dz dx by dz. Okay. So if I write dx by dz would be, I think, x, and this will be, I think, this is minus 1 upon x, this will be x square, and then this will be x. Is that clear? So it will give me 1 upon x square d2y upon dz2 minus 1 upon x dy by dz. So if I want to write my x square d2y upon dx2, if I want to write my x square d2y upon dx2 plus x2, it is equals to writing d2y upon dz square minus some x is, what is happening? कुछ तो गलती कर रहे हो, चेक करो उसको फटाफट से. I think there is a mistake somewhere. Minus 1 upon x. देखो हमने क्या किया, इफ आई वांट टू डिफरेंशिएट इट इनसाइड, तो मैंने 1 अपॉन x को बाहर किया, d by dz तो जगह d2 अपॉन dz माइनस 1 अपॉन x तो ऑलरेडी बाहर चल रहा था. आई विल राइट d by dz ऑफ 1 अपॉन x dy by dz. I think this is clear. So if I write minus 1 upon, ये तो हो गया clear. Second part is minus 1 upon x, and if I write it in, इसको थोड़ा ढंग से कर देते ना, गलती करने से अच्छा इसको ढंग से. तो what I will have, what I will get, this has been done. So now this has to be differentiated. This will be like d by dx of 1 upon x, and then I have dx by dz, and then I have dy upon dz. Okay. Now, if I solve this particular thing, I will get this. I'm solving it here. So I will get 1 upon x. This derivative is minus 1 upon x square. Okay. And this is, I think, plus here. This I will be plus here because CF. So this is mine. And this will be, I think, x, because dz by dx was 1 upon x. So dx by dz would be x. And this would be dy by dz. So 1x cancels. So I'll get minus 1 upon x square. So x square goes there. So it will come as dy by dz. Is that clear? So what you can do, whenever you have such differential equation, these are called as Cauchy-Euler differential equation. By a suitable transformation, that is x is equal to e to the power z, you can transform this variable coefficient differential equation into a constant one. So it will be like d bar into d bar minus 1 by plus d bar y equal to 0, where d bar is d by dz. Is that clear? You can see here. Bharat, is that clear? So if you want to write x dy by dx, it will be dy by dz. So instead of writing dy by dx, I'm writing d bar y. D bar y means d by dz of y. Is that clear?
Yes, sir.
And similarly, x square d2y upon dx2, I have written as d square minus 1, d bar square minus d bar y. Is that clear? So overall, I would say that this particular differential equation can be written as d bar square y is equal to 0, because this particular term will go on 0. Are you getting my point? This will get cancelled. So the solution of this particular differential equation can be done using Cauchy-Euler equation. Now, the first thing is I already know that my Green's function satisfies my initial the condition itself. So my Green's function would satisfy my my differential equation. So if I write my Green's function for this, what I would get, I would simply get two solutions. One would be a plus bz, and second would be c plus dz. Is that clear? Is that clear? This is only linear solution, isn't it? So a plus bx and c plus dz. And I know that also, don't forget this. At times people do forget this. So this is in z, you have to write in x also. So z will be equals to what? It will be equals to ln x. So eventually, if I want to write that my what would be my Green's function? So Green's function would be equal to, in terms of x and z, x, it will be equals to what? It will be equals to a plus, sorry, it will be equals to a plus b ln x for all x lying between, I think, what are the conditions given to you? 0 and 1. So for all x lying between 0 and zeta, and for all x lying between zeta and 1, my thing would be c plus d ln x. And you will see that I have not included 0 because ln x is not dependent 0. Okay, is that clear? Now the second thing is my Green's function would also satisfy the boundary conditions. The first boundary condition that is given to you is that the yx should be bounded as x tends to 0. So I know that as my x tends to 0, so as x tends to 0, I know that ln x goes towards minus infinity. So if you see the graph of ln x, the graph of ln x is this way. So you know that as x tends to 0, your ln x goes towards minus infinity. So it suggests me that your b should be equal to 0. Otherwise, it will never be bounded. Is that clear?
Yes, sir.
Okay, the first thing is that your b must be equal to 0. The second thing that is there, second condition second condition is there, which suggests that y1 should be alpha dash 1, alpha y dash 1. So y1 should be alpha dash y1. So if I use these condition, what would be my conditions? Condition number 2 suggests me that my Green's function at 1 is equals to the alpha times derivative of Green's function at 1. So this suggests, I think g1 comma zeta would be equal to c plus d, would be equals to alpha. The derivative is c, if I'm not wrong. Again, see that if there is some mistake. G dash 1 comma zeta, अच्छा sorry, यहाँ पे d आएगा. सॉरी यहाँ पर क्या आएगा, जी डैश 1 कॉमा जीटा है ना, तो यहाँ पे ये सॉरी मैं ये देख रहा था. सो अगर डेरिवेटिव करेंगे तो कितना आएगा, सी का हो जाएगा 0, इसका हो जाएगा डी अपॉन एक्स, सो इट इज अल्फा डी. और अगर जी 1 कॉमा जीटा लेंगे तो बी 0 हो जाएगा. सॉरी, अच्छा यहाँ तो देखना ही ना, यही देख. सो आई थिंक 1 लेंगे तो ये 0 हो जाएगा, दिस विल बी आई थिंक सी, सो इट विल बी सी इक्वल्स टू अल्फा डी. इज दैट क्लियर? सॉरी, क्या उस पर ध्यान चला गया. फर्स्ट, these are the two conditions that we are getting from the by satisfying the homogeneous boundary condition for the green function. Is that clear?
सर जी डैश में करेंगे तो log x का 1/x नहीं आएगा.
log x 1/x आएगा, और x की जगह 1 रखोगे तो क्या आएगा, d upon 1 आ जाएगा.
अच्छा अच्छा. यस सर.
है ना, ठीक है. So third condition that we knew was that g must be continuous, so it must be continuous at x also, sorry, zeta also. Since it is continuous, log x is a continuous function, no issues. Log x is also a continuous function, so this is continuous here, it is continuous here, but only problem may arise at zeta itself. So that also we have to see. So accordingly, I will write my a plus b ln zeta should be equals to c plus d ln zeta. Is that clear? And the fourth property should be the derivatives at zeta plus minus the partial first order derivative at zeta minus must be equal to minus 1 upon, I think, 1. कहाँ चला गया आगे, पीछे जाए वापस से. इनिशियल कंडीशन क्या तरीके थी, अच्छा ये रहा. सो यार दिस इज x ना, इसको मत भूल लेना. इनिशियल कंडीशन कौन सी, ये तो मैंने बनाई है x को मल्टीप्लाई करके. ओके, सो इट विल बी लाइक p naught zeta. So this will be like zeta only, because this is 1 upon x, right? Like, are you getting the point? This was x d2 upon dx2.
Yes sir. Yes.
Okay, so these four conditions we are going to solve in the next lecture, because the time is getting over. So meet you in the second lecture. Is that clear?
Yes sir.